네, 이어서 2부 두 번째 발표로 이어가도록 하겠습니다. 타쿠지 시라사와님인데요. 일본의 시라사와 항노화의학연구원 원장이시자 국제예방의학협회 회장이십니다. 오늘의 발표 주제는 알츠하이머성 치매와 폴리코사놀에 대해 발표해 주시겠습니다. 박수로 맞이해 주시기 바랍니다.
Thank you very much for President Lee, also the organizer committee, and also our Professor Cho invited me here in the beautiful symposium. It is for maybe 7 years, first time in 7 years to visit here Seoul, but the first visit in South Korea was 1994, 30 years ago. And I visited a small town, Chuncheon. It's 100 kilometers from here, and there's a university there. And one of my friends started the basic research center focusing on the biology of aging. And I was invited and speak a talk about the oxidative stress. Because oxidative stress plays an important role in the cellular aging. And this cellular aging is quite related to the age-related diseases such as Alzheimer's disease. So if we can control the aging process, I mean the oxidative stress, defensive oxidative stress, we can control the Alzheimer's disease. So it may lead to the prevention of the Alzheimer's disease. And 30 years after that day, I'm talking about the same keyword here. We have the longevity. And I talked about the result of the control of the aging process. Its outcome is a healthy longevity. And I'm very happy to talk about the research result of the Alzheimer's disease for last 30 years. So Alzheimer's disease, when I started the research on Alzheimer 1990, and at that time it was not so popular. But at that time, many scientists think that the Alzheimer's disease of the 20th century, but now everybody recognizes that it's a disease of the 21st century, this century. And it is very simple calculation that the population aging and the number of the Alzheimer's disease patients increasing. And so the same thing happening in the United States, also in Japan, and also Europe, and also in this country. So the population is aging. That is a simple reason why the number of the Alzheimer patients is increasing. So the symptom of the Alzheimer's memory loss, but this pathology, neuropathology, is spreading from the parietal region to the temporal region and frontal lobe cortex. So they're gonna show a variety of symptoms, not only memory loss, but loss of orientation, loss of emotional control, and so this is bunch of symptoms they have. But pathologically, before the symptom appeared in a patient, the brain pathology, neuropathology suggested that the first amyloid plaque appeared more than 20 years before the symptom began. So if the patient developed memory loss at the age of 75, maybe he developed the first amyloid beta plaque at the age of 45, maybe 25 or 30 years earlier than the symptom began. This is an MRI scan, and actually, this is the advanced case that he lost the majority of the majority. I mean more than 75% of the neuron has already lost in his brain. Compared to the control. If you, this is, I opened the clinic specialized for the treatment of Alzheimer's disease in 2018, 7 years ago, and I'm treating a bunch of ApoE4 patients. As you know, ApoE4 is a major risk factor to develop Alzheimer's disease. So the homozygous ApoE4 is 10 times more, incidence of the Alzheimer's disease. So this is actually a doctor, medical doctor, 59 medical doctor. But he cannot diagnose anymore. It's a young onset, Alzheimer's disease. If you look at the cerebral cortex, all of the cerebral cortex, including the parietal lobe and the frontal lobe and also the temporal lobe, he has already lost a bunch of neurons. So the brain doesn't function because of the loss of the neurons. And so this is reconstructed in silico from the two-dimensional MRI scan. So we can cut anywhere and precisely analyze the morphology of the Alzheimer's disease. And I developed in silico model of the 3D structure of the MRI scan. I will show some video which shows how this technology advanced to evaluate Alzheimer's disease here. Oh no, I'm sorry. This is a movie, and maybe you can put somewhere. You can make this Yumi to run. This is the PowerPoint here. You can push somewhere, and this is a movie. Can you run that? Okay, you are running this one? No? You operating? No.
I think it's in the back.
Ah.
But they're using the PDF, so that's why.
Oh, okay. Okay. Oh, this is a funny movie. I will show you later. You may be interested in. So the two kind of pathological hallmark or neuropathologists found that one is senile plaque, and the other is tangle inside of the neuron. And the senile plaque accumulate outside of the neuron in the matrix of the brain. And in 1980, a biochemist examined the structure of the senile plaque. And the senile plaque composed of the amyloid beta peptide. That is a very small peptide composed of 40 or 42. And also, biochemists analyze the structure of that tangle, and it's composed of the abnormally phosphorylated, tau protein. And this, tau protein is abnormally phosphorylated. So the abnormal some scientists imply that the abnormal phosphorylation maybe is pathological. But if you look into the time course, clinical course, pathological course of the change, pathological change, the accumulation of the amyloid beta precedes the phosphorylation of the tau. So many scientists think that the preceding event may be the cause, and the following event is a result. So still we have a discussion which is more important, tau phosphorylation or the A-beta accumulation. But many scientists think that the accumulation of A-beta, amyloid beta, is the first step to start this neurodegenerative disease. So, as shown here in this slide, we have the familiar case of Alzheimer's disease. So the 5% of the Alzheimer's disease has a family history, and a mutation may play an important role to develop the Alzheimer's disease. And several mutations found in 1990. That's the mutation was found in the gene called amyloid precursor protein. So in 1995, two more mutations found called presenilin. The presenilin is the component of the gamma secretase here. So majority of the mutation, co-localized in this slide, suggesting that the one of the cause start point is the processing of A-beta protein. A-beta protein is 40 or 42 peptide, but originally its membrane portion of the big membranous protein called amyloid precursor protein. And this physiological function of amyloid precursor protein is still undefined. But the condition that this A-beta protein pop out from the membrane has two enzyme work. One is beta secretase here, and the other is gamma secretase, and they pop out the A beta peptide. So many scientists think that in 2000, especially Dr. Seiko in Harvard Medical School, think that pop out of the A beta peptide is a pathological process, and if we can inhibit this gamma secretase or beta secretase, that is the final answer. The drug treatment can apply to this disease, but we found that A beta peptide was found in a normal subject with no dementia. So the next, okay, this is a monomer of A beta, but A beta becomes dimer and trimer, and also trimer. If more one monomer bind to this trimer, and are going to form the tetramer and the pentamer, and this is called oligomer. And the researcher found that only the oligomer are neurotoxic, and the monomer don't, no effect. Also, the A beta fibril, which has no toxic effect, so the oligomerization may play an important role for the neurotoxicity and synaptic growth. So, if we can block that process, we can control the oligomerization. So this may be the most important pathological, pathway. So one of the way to think about the blockage, inhibition of the oligomerization, one is a molecular chaperone. So A beta is very hydrophobic protein. So the structure is originally, localized in the, lipid bilayer. It means it's hydrophobic. And the molecular chaperone should be the, hydromorphic molecule. And 3 molecular chaperone has been reported. And all 3 chaperone can cause amyloidogenic disease because they are hydrophobic structure, molecular structure. And one is transthyretin and the other is cystatin C, but the third one is ApoA1 that we are discussing in this morning for this molecule. And I think this is a 3 endogenous molecular chaperone that can inhibit the oligomerization of the A beta molecule. And if you look at, you have the specialist for this, I'm not a specialist, but ApoA1 molecule can have the structure to block the A beta oligomerization, like cystatin C or the transthyretin. Maybe a similar mechanism, and I'm very interested in the structural biology, how to block the oligomerization. Anyway, it is Professor Cho's slide that I'm kind of interested that polycosanol, especially human polycosanol, can inhibit the cholesterol ester transporting protein CPTP, and the mechanism of the block may be the length of the lipid molecule, and that can explain why the ApoA1 and also the structure of the trimer, A beta trimer. If we can simulate in silico the blockage, we can make some chemical compound, a similar chemical compound that can inhibit the oligomerization of the A beta molecule. But another evidence also we have in the previous presentation, she talked about blood-brain barrier breakdown. Also, polycosanol can influence or impair the breakdown of blood-brain barrier. Also, the transgenic mouse study suggested that the accumulation of A beta is blocked in the transgenic mice which developed Alzheimer's disease. And if you look at the A beta molecule is inhibited, accumulation is inhibited. Also, the microglia activation is also inhibited. So this is a slide which summarizes that we have the evidence on the HDL molecule can be applied for the Alzheimer's treatment. One is amyloid beta accumulation. The other is repair of the blood-brain barrier. Also, the activation of microglia is inhibited by the polycosanol. So we have make sure which mechanism can be applied for the treatment, to establish the treatment of Alzheimer's disease. This is summary slide, and thank you for your attention. 감사합니다.
네, 타쿠지 시라사와 원장님의 발표였습니다. 이어서 질문 받도록 하겠습니다. 원장님께 궁금하신 점이 있으신 분은 손을 들어주시면 저희가 마이크 가져다 드리도록 하겠습니다. 네, 질문 있으신 분은 손을 들어주시면 감사하겠습니다. 네, 마이크 가져다 드리겠습니다.
Good afternoon, sir. I'm Astos from Radar Research Institute. So far, means you use the polycasanol to treat the Alzheimer disease. That means that polycasanol is increasing ApoA1, and due to that, we are getting that the inhibition of that the AB and getting some treatment for the Alzheimer. Is it like this one?
Unfortunately, I'm not doing the experiment of Alzheimer's disease, but I am thinking the theory how this polycosanol can apply for the Alzheimer's treatment, or maybe the prevention of the Alzheimer's disease.
Okay. Thank you. Thank you.
네, 감사합니다. 혹시 또 질문 있으신 분 계시면 손 들어주시기 바랍니다. 네, 마이크 가져다 드리겠습니다.
Thank you very much for your excellent talk. I'm Dr. Uehara from Japan. Could you tell me your final slide? So you showed the possibility for the polycosanol to inhibit the activated microglia. So could you tell me the more detail for that?
Yeah, it's evidence that the transgenic mice are treated with polycosanol, and the pathology suggested that activated microglia is transformed to inactive type. So we don't know the mechanism, but some mechanism there, and we should study more.
네, 또 다른 분의 질문이 있겠습니다.
I'm Hidoe from Radio Japan, and I'm very interested in your presentation in the HDL and Alzheimer disease. As we all know, that lower HDL will cause not the causal reason, not the causal factor, but the associated factor. So, how do you think if is the higher the HDL will be the better for the Alzheimer disease prevention of the Alzheimer disease? And the second question is, how much the higher HDL concentration in the blood should we maintain for prevention of the Alzheimer disease?
Yes, it's a good question, and polycosanol is the only intervention to do that. So we have to do that, intervention study to clarify that if this higher level of HDL can prevent the development of Alzheimer's disease, or can improve the symptom of declined cognitive function.
Thank you very much.
네, 이렇게 해서 질의응답 마치도록 하겠습니다. 수고해주신 타쿠지 시라사와 원장님께 박수 부탁드리겠습니다. 3부 시작에 앞서서 양해 말씀 드리겠습니다. 2부 두 번째 순서였던 타쿠지 시라사와 원장님의 발표에서 영상이 열리지 않는 오류가 있었습니다. 따라서 원장님을 다시 무대에 모시고 해당 내용 간략하게 듣고 3부 시작하도록 하겠습니다. 원장님 무대 위로 모시겠습니다. 박수 부탁드리겠습니다.
I apologize for skipping my interesting video. But before that, I opened a clinic in 2018, which is specialized for Alzheimer's disease. And the MRI scan is usually based on a two-dimensional one, but Alzheimer's disease is the disease of the cerebral cortex. And it should be the structure of the cerebral cortex should be analyzed in three-dimensional. So I modified the program which can make 2D to 3D in silico. So in that case, we can. I'm going to introduce you the journey of inside of the brain with endoscope. Okay, I will show you this one. Okay, this is a three-dimensional model of the Alzheimer's ApoE4, 59-year-old, and 1 millislice of sagittal section can, reconstructed in silico. So you can cut anywhere you like. Also, you can put the camera and also the light inside of the brain. Here is a hippocampus in silico. You can see how the hippocampus is atrophied in the endoscopic view. That is the left hippocampus. Also, it's the neck of the right hippocampus, and you can see everywhere 1 millimeter region of the Alzheimer's brain. And after I analyzed this 3D reconstruction and going back to the 2D dimensional conventional MRI scan, and MRI scan cannot analyze the structure of the atrophied, Alzheimer's disease, because the cerebral cortex is a 3D structure, and you cannot judge the disorganization of this, cortical structure by two-dimensional MRI scan. I skipped this. Thank you.
네, 교수님 감사합니다. 교수님께 박수 부탁드리겠습니다.